Imagine trying to describe something just so completely unlike anything you've ever seen before. No waves, no particles, certainly no billiard balls.
Something else?
Something else entirely. And that feeling, that challenge, that really captures what we're trying to get into today.
Yeah, because the universe, especially when you zoom way, way down, it just doesn't play by the rules our everyday experience sets up for us.
Absolutely. So in this deep dive, we're digging into what our main source material actually calls the only mystery of quantum mechanics.
Yeah.
It's this phenomenon, I guess, that's so deeply strange that even the experts don't fully understand it in the way we normally understand things.
Right. Our goal isn't really to give you an intuitive how it works, because that's sort of the problem. It isn't intuitive.
Okay.
But we can tell you that it works this way and show you the basic peculiarities, the core weirdness that applies to all quantum mechanics.
So yeah, get ready to have your intuition stretched a bit, maybe quite a bit, because we're talking about how matter and light behave on the smallest scales.
It's truly foreign to our macroscopic world.
Okay, so let's pin that down. Quantum mechanics. What exactly is it describing? What scale are we talking about?
So fundamentally, it's the description of how matter and light behave in all their details, but specifically on the atomic and subatomic scale.
Right. Electrons, protons.
Electrons, protons, neutrons, photons, the fundamental bits. And their behavior is just, well, it's quantum. It's unique.
And the thing our source really hammers home is that these tiny things behave like, and I'm quoting here, nothing that you have any direct experience about.
Exactly. Not waves, not particles, not clouds, not billiard balls.
Lisa says it is like neither.
Yeah. And that's crucial. I mean, historically, scientists really struggled with this, didn't they? Light wasn't particles. Waves. Back and forth for centuries.
And electrons seemed like particles.
Until they didn't. Early 20th century experiments started showing light acting like particles sometimes, electrons acting like waves sometimes. It got confusing. Now, basically, we've given up trying to force them into those old boxes. They're their own thing, a quantum thing.
But hang on, there's a bit of good news in all this complexity, right? It's not like every single particle has its own bizarre set of rules.
That's true. That's maybe the one simplifying grace here. The quantum behavior of all these atomic objects, electrons, protons, photons, it's fundamentally the same.
Oh, okay.
They all have this particle wave nature, whatever name you want to give it. So if we dig into electrons, which is what we'll mostly use as our example.
We're actually learning about how photons and everything else work too.
Pretty much. The fundamental principles apply across the board.
Okay, so that early 20th century must have felt pretty chaotic for physicists then, trying to piece this together. When did a sort of consistent picture emerge?
It really was. The first, say, 25 years were full of confusing results piling up. But then around 1926, 1927, things clicked.
Schrödinger,
Heisenberg. Born, they developed a consistent mathematical description. But, and this is important, even for them, it still felt deeply weird, mysterious.
Why? If they had the math.
Because all our intuition, everything we feel about how the world works, comes from large objects, stuff we can see and touch.
Right.
To understand the quantum world, you have to approach it differently, more abstractly, using your imagination almost, guided by the math.
Okay, so to really feel how different this quantum world is, let's set up a comparison, like a baseline, using things we do understand from everyday life.
Good idea. Let's use the thought experiment our source focuses on. Imagine an apparatus. You've got a source shooting out some kind of stuff.
Okay.
Then there's a wall, but it has 2 holes or slits in it. Behind that, a backstop to catch whatever gets through.
Right.
And crucially, a detector you can move along the backstop to see where the stuff lands.
Got it. Gun, wall with 2 holes, backstop, detector. What's the first kind of stuff?
Let's start simple. Bullets. Like from a machine gun, maybe one that sprays a bit randomly. What do you observe?
Okay, well, bullets arrive as definite things, right? Lumps. Always a whole bullet, never half a bullet.
Exactly. Distinct, identical lumps. If you fire them slowly, one by one, your detector only ever registers one hit at a time, a single click.
So we'd measure the probability, right? The chance of a bullet hitting a certain spot X on the backstop.
Precisely. And what pattern do you expect if both holes are open?
Well, it seems obvious. The chance of hitting a spot with both holes open should just be the chance of hitting it if only hole 1 was open, plus the chance if only hole 2 was open. They just add up.
Perfect. P12 equals P1 plus P2. That's the formula.
Right. So there's no interference. A bullet goes through hole 1 or hole 2. The paths don't interact. The chances just combine. Simple. Logical.
Exactly what you'd expect for classical particles. Okay, hold that thought. Now let's switch the stuff completely. Water waves.
Okay, like in a ripple tank. Wave generator, same wall with 2 holes, detector measures. Intensity, like the energy of the wave.
Right, intensity or energy. And the first big difference.
No lumps? Waves aren't lumpy. The intensity can be small, large, anything in between. Your detector just measures how strong the wave is at that point.
Good. Now, what happens to the pattern on the backstop when both holes are open for water waves? Is the intensity I12, just I1 plus I2?
No, definitely not. You get that classic wave pattern, peaks and troughs, places where the intensity is really high and places where it's almost zero.
And that's interference. Explain that.
Well, the waves spread out from both holes. Where they meet in phase, crest meets crest, trough meets trough, they add up constructively. Big wave, high intensity.
And where they meet out of phase.
Crest meets trough, they cancel each other out destructively. Small wave, low intensity.
Yeah.
Or even nothing.
Right, so the intensities don't add, but the underlying wave amplitudes do, and the intensity depends on the square of that combined amplitude. That gives you the interference term.
Yeah, it makes sense for waves. They spread, they overlap, they interact. That's just what waves do.
Okay, so we have 2 clear baselines. Bullets. Distinct lumps, probabilities add, no interference. Water waves. Continuous intensity, complex interference pattern.
Got it. Got it. Bullets add, waves interfere. Now for the main event. Electrons.
Electrons, same setup. Electron gun fires them, wall with 2 holes, backstop, movable detector like a Geiger counter that clicks for each electron.
Now, you mentioned this as a thought experiment.
Yeah, a crucial point. Actually, building this exactly as described for electrons would be, well, incredibly difficult, maybe impossible because the scale is so tiny.
But the results are known.
Oh, yes. These effects are confirmed in countless real experiments that show the same fundamental behavior, just maybe in different setups. So imagine we fire those electrons one by one, slowly. What does the detector register?
Well, based on what you said earlier, it should be like the bullets, right? Distinct arrivals, sharp clicks. Always a whole electron, never half a click.
Exactly. Always a full click, always one electron at a time. It arrives like a particle. Lumpiness confirmed.
Okay. But then what happens to the pattern when both holes are open? Does P12 equal P1 plus P2?
Ah, here it comes. No, it absolutely does not.
What?
When both holes are open for electrons, the probability distribution where those individual clicks build up over time looks exactly like the interference pattern from the water waves.
You're kidding. Peaks and troughs, places where fewer electrons land with both holes open than would land with just one hole open.
That's precisely it. There are spots on the backstop where opening the second hole actually stops electrons from arriving, even though plenty would get there if only the first hole or only the second hole were open.
But how? They arrive like particles, distinct lumps. How can their probability pattern be like a wave?
That is the paradox. That's what our source calls the only mystery. They arrive like particles, but their probability is distributed like a wave.
So they behave sometimes like a particle and sometimes like a wave.
That's the phrase often used. And it forces us to question that seemingly obvious idea. Proposition A, each electron either goes through hole 1 or it goes through hole 2. If that were true, the probabilities would just add, but they don't.
So proposition A must be false. But how can a lump, a single thing, not go through one hole or the other? That just breaks my brain.
It breaks everyone's classical intuition. As the source says, it is all quite mysterious, and the more you look at it, the more mysterious it seems. Nature's playing by different rules here.
Okay. So what happens if we try to peek? If we try to actually watch which hole the electron goes through?
Right. Let's modify the experiment again. Put a light source right behind the wall between the holes. Electrons scatter light, so if one goes past hole 1, we should see a flash near hole 1. If it goes past hole 2, a flash near hole 2.
Makes sense. So what happens now when we run the experiment? We listen for the click at the backstop, and we watch for the flash at the holes.
And here's the next stunner. Every single time you hear a click an electron arrives, you also see a flash of light. Every time. And that flash is always near either hole 1 or near hole 2, never both at the same time.
Wait. When we look, they do go through one hole or the other. Proposition A is true now.
Experimentally, yes. When you watch, you can definitively say that electron went through hole 1 or that one went through hole 2.
Okay, reality restored. Wait, there's a catch, isn't there?
There's a huge catch, the kicker. When you watch the electrons and confirm they go through one hole or the other, the interference pattern completely vanishes.
Gone.
Gone. The new probability distribution, let's call it P12, is now just P1 plus P2. Exactly like the bullets, no interference whatsoever.
And if you turn the light off?
The interference pattern immediately snaps back into existence.
Wow. So the act of observing just looking destroys the quantum weirdness. How?
Well, the source explains it as disturbance. The light you use to see the electron isn't passive. A photon of light has to bounce off or scatter from the electron for you to detect it.
And that bounce.
Gives the electron a jolt, a little kick. And that kick is apparently just enough to mess up its trajectory and destroy the delicate phase relationship needed for interference.
Okay, but what if we try to be really gentle? Like, dim the light way down. Use fewer photons.
Good thought, but think about light itself.
Yeah.
It's also quantum, right?
Yeah.
It comes in lumps, photons.
Ah.
So dimming the light doesn't make the flashes gentler. The flashes, when they happen, are always the same sized flash. Dimming just means fewer photons are available, so some electrons will sneak past without scattering a photon. They go unseen.
And what happens then? With the seen versus unseen electrons?
You get a mixed result. The electrons you do see, the ones that scatter a photon and get disturbed, their distribution shows no interference, P1 plus P2.
Right.
But the electrons that slip through unseen, the ones that aren't disturbed by a photon, if you could somehow track just them, their distribution still shows the interference pattern.
It's like the electron knows if it's being watched.
Yeah.
Or even if there's just the possibility of being watched effectively.
It certainly seems that way. It reacts to the potential for information being gathered. Okay, so what about another approach? Instead of dimming, use gentler light with a much longer wavelength.
Does that work? Longer wavelength means less energy, less momentum per photon, right? So smaller jolt.
Exactly. A longer wavelength photon gives the electron a much smaller kick when it scatters, so less disturbance.
So maybe the interference pattern survives.
But physics gives with one hand and takes with the other. Remember how microscopes work. The wavelength of light limits your resolution.
Right. You can't see details smaller than the wavelength.
Exactly. So as you make the light's wavelength longer and longer to reduce the jolt, you simultaneously lose the ability to tell which hole the electron went through. The light wave is too spread out to resolve the two closely spaced holes.
Oh, so you can't know the path anymore.
Precisely. And here's the absolutely crucial point. The interference pattern only starts to reappear when the light's wavelength becomes so long that you have zero chance of determining which hole the electron passed through.
Wow.
The disturbance becomes small enough only when you completely give up the which path information. You can have one or the other, but not both.
This leads somewhere fundamental, doesn't it? This trade-off.
It leads directly to one of the cornerstones of quantum mechanics, Heisenberg's uncertainty principle. He saw this kind of inescapable trade-off and proposed it as a fundamental limit on what we can know.
What does the principle state formally?
In this context, it basically says, it is impossible to design an apparatus to determine which hole the electron passes through that will not at the same time disturb the electrons enough to destroy the interference pattern.
And nobody's found a loophole.
Nope. Not in almost a century. It's not about building better gear. It seems to be a fundamental rule woven into the fabric of reality.
So we're forced into this really careful way of talking about it?
Extremely careful. The source calls it a logical tightrope. If your setup can tell you which hole the electron went through, fine. You can say it went through one or the other. The interference is gone anyway. But if there's nothing in the experiment that determines the path, if you don't know and can't know which hole it took, then you cannot say it went through one or the other. If you do, your predictions about where it will land, the interference pattern, will be wrong.
You have to treat it as if it somehow explored both paths simultaneously, even though it arrives as one lump.
That's the counterintuitive picture quantum mechanics forces on us.
This also explains why we don't see interference with, say, bullets, right?
Yeah.
Even though technically everything has a wave nature.
Exactly. For a macroscopic object like a bullet, its quantum wavelength is absurdly small, trillions and trillions of times smaller than an atom.
So any interference pattern would be
Impossibly fine. Any detector you could build would span millions or billions of those tiny wiggles. It would just average everything out, giving you that smooth, classical P1 plus P2 curve. The quantum effects are washed out by the sheer scale.
And Heisenberg knew this principle was critical for quantum mechanics itself.
Oh, absolutely. He realized that if you could somehow violate the uncertainty principle, measure position and momentum more precisely than it allows, or figure out the path without destroying interference, the whole logical structure of quantum mechanics would fall apart. It would lead to contradictions.
But it hasn't collapsed.
It hasn't. So the principle stands as this fundamental guardrail protecting the consistency of the theory. It's a strange reality, but a consistent one.
Okay, so let's try to boil this down. What are the absolute core rules, the principles of quantum mechanics that come out of this experiment?
Our source highlights 3 key things. First, probabilities come from amplitudes. The probability P of any event is the square of the absolute value of a complex number called the probability amplitude, phi. So P equal phi 2.
Okay, probability is amplitude squared. What second?
Second, amplitudes add for alternatives. When an event can happen in several alternative ways, like an electron going through hole 1 or hole 2 and you don't observe which way.
The amplitudes just add up.
Right. The total amplitude is phi 1 plus phi 2, and then you square it to get the probability. P equals phi 1 plus phi 22. That sum inside the square is what creates the interference term. That's the quantum magic.
Okay, and the third principle?
Third, probabilities add when you know the path. If you do perform an experiment that determines which alternative was taken, like watching the electrons with light,
the interference vanishes.
The interference vanishes. The total probability is just the sum of the individual probabilities. P equals P1 plus P2. You lose the amplitude addition because the observation collapsed the possibilities.
Amplitude squared, amplitudes add for unknowns, probabilities add for knowns. That's it.
That's the fundamental computational rule.
And here's maybe the most profound part for me. You said earlier, the source emphasizes no one has found any machinery behind the law. We don't know why amplitudes add this way.
Correct. We can describe that it happens, we can use the rules to make incredibly accurate predictions, but we can't explain the mechanism in terms of smaller, more familiar parts, like gears in a clock.
So physics has kind of given up on that deeper why for quantum events.
In a sense, yes. It's a huge shift. Classical physics was all about deterministic prediction. Set things up, and you know exactly what will happen.
But quantum mechanics
Can only predict probabilities. The likelihood of different outcomes for a single electron, say. It's a fundamental retreat from that old ideal of perfect prediction. But as the source notes, nobody has found a way around it. This seems to be how nature operates.
What about those ideas like maybe there are hidden gears, hidden variables inside the electron telling it which way to go? We just haven't found them.
Yes, the hidden variables idea. It's tempting. Maybe the electron does have a definite path determined by some internal state we can't see, but the experiments contradict it. If hidden variables were dictating a definite path, hole 1 or hole 2, even one unobserved, then the overall pattern would have to be P12, P1 plus P2, just like bullets.
Because each electron would really be going through only one hole, whether we knew it or not.
Exactly. But that's not what we see. We see interference. P12 equals phi 1 plus phi 22. The results force us to conclude that, unless observed, the electron doesn't have a definite path in the classical sense.
So the puzzle is impossible to beat. This is just the way nature really is.
That's the conclusion physicists have been forced to accept. It's a completely different reality from our everyday intuition.
Wow, what a deep dive that was. We've gone right into the core strangeness of the quantum world. Particles that arrive like particles but distribute themselves like waves.
Observations that literally change the outcome, seeing how the simple rules for bullets and water waves just completely fall apart for electrons.
And uncovering that fundamental interference at the heart of it all. Plus the uncertainty principle standing guard, making sure it all somehow hangs together.
Yeah, it forces you to really reconsider what reality even means at that level.
Absolutely.
Yeah.
So here's a final thought to leave you with.
Yeah.
Consider this universe where, at its very foundation, certainty just dissolves into probability, where the simple act of knowing something, of observing it, fundamentally changes what happens.
If things only seem to choose their path or state when we measure them, what does that imply about cause and effect as we normally understand it? About the nature of an objective reality existing independently of us?
It's not just about weird little particles. It feels like it touches on the very fabric of existence. So what new questions does this deep dive raise for you about the world, and maybe even our role in observing it?